Good afternoon, everyone. This is Juma Ghosh, curator at Nehru Science Centre, Mumbai. I welcome you all to our online lecture today. We have come to the end of our week-long online lecture series organized on the occasion of International Women's Day 2021, where we try to help the students to explore various career opportunities in future if they choose to work in the frontiers of science. Today's speaker is a familiar name in the high energy physics field, Dr. Archana Sharma. She will be talking about the future opportunities for Indian girl students in Cern project. Let me take this opportunity to introduce Dr. Sharma. Dr. Archana Sharma is a principal staff scientist at the Cern laboratory in Geneva, Switzerland. She has been active in the field since 1989, mainly working on the instrumentation. She is the pioneer of simulations and experimentation on gaseous detectors over the last 3 decades. With a degree in nuclear physics from Benares Hindu University and a PhD degree from Delhi University in 1989. She started her career on the instrumentation for high energy physics, and she obtained a DSc degree from the University of Geneva in 1996. Dr. Sharma has worked on several Cern experiments, both on R&D, designing, prototyping, and running several laboratories for construction, installation, commissioning of large-scale gaseous detectors. She is founder and project manager of the CNS-GEM collaboration, which brings a new technology, gas electron multiplier, for exploiting one of the most sensitive detectors with the highest discovery potential to CNS. She has also been actively facilitating the capacity building in India via her Live Lab Foundation for Education and Research based in New Delhi. Dr. Sharma was recently one of the key thematic group members on Mega Sciences for the formulation of Science, Technology and Innovation Policy 2020 at DST. Dr. Sharma has recently been appointed as the Senior Advisor for Relations with International Organizations in support of Cern's objectives of integrating and highlighting fundamental research towards science diplomacy. With these words, I'd like to thank Dr. Archana Sharma for accepting our invitation for this lecture, and I will request her to take over. Thank you.
Thank you very much for the gracious invitation and a very warm welcome to me. Thank you very much for people who are attending this talk, because I do remember that my own journey started like that, listening to other people, listening to people who so-called have made it in the field of high energy physics. And I'm very privileged to be here sharing with you whatever little I know and whatever little I have learned in my journey. So thank you, Dr. Ghosh, for this opportunity, and I will try to highlight a bit about Cern, a bit about what we do, and a bit about how every girl student in India can actually dream of becoming a research scientist, an applied scientist, an engineer, a manager, and so on at Cern in the Cern experiments. So what exactly is Cern? I think all of you know very well. This series has been very rich in terms of looking at mega science projects, in understanding what's going on in the world of mega sciences. This is a new term now, relatively new, so to speak. It has been around for some time, but now it's really highlighted in the way that projects are done over decades with hundreds and thousands of people working together. But they all have one common theme, which is that they are looking at questions for the universe. And that's exactly what we do at Cern, where we examine questions like what is the nature of our universe and what is it made of. So naturally, Cern itself is an organization, an institution which was built in Europe in 1954. The foundation was laid when many of the European scientists were running away after the Second World War to the United States. So they all came together and they made this organization called Centre Européen pour la Recherche Nucléaire, so-called Cern, although it's no more nuclear physics, it's about high energy physics or particle physics. So scientists from all around the world come together and they work in experiments at Cern and also in their home institutions back home, in their countries. So they are looking for answers to these fundamental questions that you all are also following in one way or the other in your lives, in your careers, in your science, and whatever you study in your institutions. And how do we do that? We are using particle accelerators and we are pushing the limits of technology. So I'm sure you are looking at, if you are looking at careers, you are looking at physics, physicists, engineers, accelerator physicists, technologies, technical skills, and so on. So indeed, it is a very big universe, so to speak, where at CERN, we are unlocking the secrets of the universe. And there are challenges, of course, but there are opportunities for everyone who dreams to have a career in research in particle physics. We do, of course, the research we just mentioned at the cutting edge. So we do not know yet the answers to questions like what is the technology we will use in 20 years. Just like I didn't know anything about this 20, 30 years ago, it took 20 years to come to a decision, what should we use as technology for the experiment that's going on today or will be done a decade later. So these are very long projects and we need to prepare our ground in such a way that we are always at the cutting edge. Whatever we do here at CERN has a very far-reaching societal impact. I do not have to tell you, that's another course or another lecture about the societal impact of what we do in particle physics, particularly simply because it is a mega science and a mega project, and the implications go far beyond the classroom, far beyond the laboratory, to the whole world. This is a compelling engagement to the entrepreneurs among you who might want to pick up some technologies from here and take them into the society. So we will go into those kind of details as well. The pictures you see here are on the left of your screen. You see the actual Large Hadron Collider, so to speak. Large is very big, it's 27 kilometers in circumference. And the one on the right you see is a dream for today, which is the Future Circular Collider. It is 100 kilometers in circumference. So how are we going to bridge this gap between where we are today and what we will do tomorrow? And this is not only tomorrow, but it is in the decades to come. So 2040s and 2050s will be the time for the Future Circular Collider, and people who are in their 20s today will be the leaders of these projects. So you need to literally engage and look at exactly where you can play a small role or a very big role in these projects. So yes, at CERN, we do fundamental research. This is, of course, a driver of innovation, because if you only Google kt.cern, that is knowledge transfer.cern, you will see the number of technologies that are available for technology transfer and for conversion into societal impact is immense. So it is a driver of innovation, and yet these mega science projects are looking at physics questions. So this research can only thrive in an international collaboration. When people come together and when governments come together and they can invest big money, so to speak, into big science, because we do not know what are the dividends today, but tomorrow we will be very happy that we were a part of these very big experiments. Of course, you may have heard the words about Higgs boson, Large Hadron Collider I already mentioned, birth of the web, antimatter that was created for the first time, the most expensive material on the planet, and of course the upgrade of the Large Hadron Collider is called the High Luminosity LHC. These are projects that are ongoing at CERN, and of course the Higgs boson, who doesn't know? So on Women's Day, first of all, congratulations and my very best wishes to all the women and girls among you who are here with me today, simply because the potential that we carry is unimaginable. And no one can undermine a woman if she has made up her mind that what she is going to make as a contribution in science or in the world in any way for that matter, in any particular discipline. But at CERN, certainly there are women, there are exemplary women who are making history. So the first name that will come to mind is, of course, Fabiola Janotti, whom many of you might know. She is also an experimental particle physics. So she has studied physics in her college and school and the university. She did her PhD as well, just like many of us have done. And she, of course, I will not go into the whole history. You can just Google and you'll find her on Wikipedia. But the big credit goes to her that she led an experiment, Atlas, into discovering the Higgs boson. She is the first woman director general of CERN, and she is the first ever director general of CERN who got a full mandate for a second term. So for 10 years, she is shaping the history of where particle physics is moving in the future. So in her words, CERN is a concrete example of worldwide international cooperation and a concrete example of peace. Some of you have visited CERN or read about CERN. You see how people work together, and there are no borders here. Science really has no borders, and we all work together for a common goal, and that is what really makes better scientists and better people, like Fabiola says. So, of course, the questions that we have been asking can impact possibly millions or even billions of lives. For why I say billions? Because simply that we are able to speak together today is a feat and a marvel of technology. And that's possible because scientists have been working in the laboratory, like at CERN, where the WWW was invented, right? So we are looking at questions, different kind of questions, looking at where did we come from, how was the universe made, what was the state of matter at the time of the Big Bang, and so on. So these are questions that we want to ask, and then we want to go back in time. So-called making a time machine at CERN, that's actually the Large Hadron Collider. So in this machine, we are recreating a very, very tiny controlled conditions in the laboratory, a very, very tiny Big Bang, so to speak, by using the Large Hadron Collider. All of you know about the current understanding of the constituents of matter. You know that matter is made out of crystals, molecules, and then if you go deeper, you will look that they are made out of atoms, and the atom itself is made out of the atomic nucleus. And inside the nucleus, of course, we have protons and neutrons, and these are also made out of quarks. And of course, the electron that completes the atom is a lepton, so to speak. Lepton and hadrons are just generic names, don't be too confused. But these are fundamental particles. And how did we come to learn about this? How did we know about this? So we tried to smash things together, and when we smash things together, we can find out what is inside whatever we are smashing. So if I take two helicopters made out of Lego, let's try to smash them, giving them some energy. What happens? They break down. The helicopters break down. We do not see really where our helicopter disappeared, but we can sort of build it back together, right? So that is the experiment that kids do all the time. And you have been actually scientists when you have been children, when you have been playing these games, right? You have always seen children breaking things and then putting them back. So these are our helicopters. They are made out of Lego, and still you see that we did not go into the basic constituents. Why? Because the energy that was given to the helicopters was not enough. So let's give a little more energy, and when we give them a little more energy, then we come to the basic building blocks of our helicopters, right? So doing these kind of experiments, scientists have actually unclassified, so to speak, or they have gone back in time and they have understood in the beginning of time what are the constituents with which you and me and everybody is made of. And theoretical physicists have been describing this very wonderfully, so to speak, in a very elegant equation that can be written on a teacup, right? So once you know you've done that, you also understand that all matter that me and you are made of, the ordinary matter is made out of leptons. The electron and the electron neutrino is what we can speak about, and the quarks, which are up and down quarks. So three quarks together make the neutron and the proton, right? And the electron comes together, and that makes then an atom. Of course, then there are other particles that have been observed, and how they have been observed by studying cosmic rays or by studying in particle accelerators. So there are three families, and you see there is the muon with the muon neutrino, and there are quarks, the charm, and a strange quark as well. And of course, there are even heavier leptons. They are called leptons, but they are heavy. The tau and the tau neutrino, and of course the top quark and the bottom quark. And of course, each particle has its own antimatter particle also, so an anti-image. Some of you might be wondering, does it really exist, antimatter? And it's actually true, because they have been observed in cosmic rays, and also they have been produced at Cern in various experiments. So how do we continue? Let's continue our smashing, and let's see what else can we do if we increase the energy. Oh gosh, what happened? Instead of having the basic constituents that we had started with, we get something completely unexpected. So indeed, we have gone back in time, just like the dinosaurs. Suppose the Lego helicopters, they are made out of, we have just given them energy. And so just using this one equation, that is E is equal to mc squared, we have given available energy enough to create something new, something we know that existed back in time but does not exist today. So it's this experiment these scientists keep playing around at Cern, where we give energy to protons in in a very controlled condition, in beam pipes, in a very tiny space. Protons are accelerated, and then they are made to collide. And when they are made to collide, using the energy is equal to mc squared equation, we are able to produce particles that existed at the time of the Big Bang. So it's incredible. We get from our protons, we get a lot of highly expected particles that come out. So let's say that we start with mosquitoes. So if we start with mosquitoes that are our protons, we get a whole lot of things coming out when a lot of energy is given to these mosquitoes. So it is simply incredible. It's nearly magical, but it can be explained by science and by all the people who have been working behind to create those equations and to create very highly expected results of these experiments. So there are the physicists, the theoretical physicists, and then there are the experimental physicists who are working on the experiment. So of course, we want to continue the experiment and try to see what more can we get. So yes, there are many, many questions. As you know, what is the origin of mass? What is the nature of dark matter? Because we know that, first of all, we exist. It means that matter has somehow superseded antimatter. It does not behave in the same way like antimatter. So there is some imbalance in the universe, and that imbalance must be studied, right? For dark matter as well, there is a lot of imbalance in what we can actually observe and what should be there. From all the measurements that have been done by cosmologists and astrophysicists, all the information that we have suggests to us that there must be something more, and that something more is dark matter, but we do not know what it is, so we need to study. And of course, the state of matter at the time of the Big Bang is that primordial plasma, so to speak, which we would like to study and which has been observed at Cern. And of course, there is an experiment that's dedicated to each of these questions. So yes, there are many, many opportunities by studying STEM. You study, of course, in school, you study STEM, and then you study nuclear physics or particle physics. In fact, now it is particle physics, and it's also called high energy physics. So yes, we have exemplary Indian women working with the experiments and the theory. This slide particularly shows you the three women who have been doing amazing contributions in the theory work that is going on at Cern. I will not have time to go into detail of every person, but I encourage you to go just on Google and just type their names. So who doesn't know Padma Shri Rohini Godbole, Nishita Desai, and Suchita Kulkarni, who are making incredible predictions for what can we measure in our experiments. And particularly for Rohini, she has contributed to the suggestions on what exactly we would be able to measure, and that was in fact confirmed when we had discovered the Higgs boson that was discovered at CERN. So there is a disclaimer I would like to mention, which is that I will not be able to do justice to all Indian girls and women at CERN, and whoever I will be able to mention, it is of course, please bear in mind, it's a partial list. So our experiments require many, many things. First of all, there is no solo game here. It is a very big teamwork and everyone has to work together. That's one condition in our field. So it's not only about being specialized, because I do not know much about accelerators. If you ask me many questions about accelerators, I wouldn't know. If you ask me about detectors, I might know something about detectors because that's what I have done over the last 30 years, right? Some people are experts in computing, and of course, we need thousands and thousands of engineers, technicians, support staff who will be able to build and operate these very complex machines. So we need these different kind of, let's say, career path of people who will help us to create this very large, the largest microscope on the planet, so to speak. That's our Large Hadron Collider. Oh, my animation is not going the right way. I'm sorry for that. But what you actually see here is an aerial view of CERN, and the Large Hadron Collider lies 100 meters below the Earth. The line, which is like a plus line in the middle, is actually, and on the left side you see Switzerland, and on the right side you see France. So our experiments really, they span literally from the time of the Big Bang, and we study the implications of what we do go up to the scale of the universe, so to speak. So yes, these experiments are located in different places. My particular experiment is in France, and it's located far away from my house, which is a bit close to the airport. You can see the airport on the bottom leftish part. And my experiment is 20 kilometers from here. So that's how it looks. There is a lake in Geneva also that is right in the center over here. The Alps are on the top, and then you look that when you go on the bottom, you see that the protons are actually circulating in the Large Hadron Collider on 100 meters below, as I mentioned earlier. And of course, the 4 experiments are located at 4 different points. The protons go around and they make the collisions. And of course, we need to be ready with our experiments to take data to be able to look at the questions that we were posing earlier. So this is a very big engineering challenge. Do I see a person anywhere in my screen? Oh yes, I do. On the bottom picture, you see a person in the middle. So that's the size of the experiments. They are like multi-storied buildings. And these multi-storied buildings are also very dense. They are not empty. Each of these stories, so to speak, they contain detectors which can track particles, or they can detect particles that we can then correlate to what happened during the collision at the collision point in my experiment. So to design something like this takes decades, so to speak. And we have had pioneering people who have been working on this from decades, from the original design. There have been different countries that have been involved, and India has played a major role in several of these, let's say, in CMS and ALICE, yes, but also on the accelerator, and I'm not going in detail there, but just to say that every piece that is built in some place in the world has to come here and match with the other piece that has come from another part of the world. So that is called technical coordination. So we need engineers, we need people who can coordinate, who can keep track of every millimeter, and not only millimeter, it has to match within 100 microns. So it is an incredible feat, and it has been done, of course, as you see. So back to looking at our experiments, we are so proud of them. So top one is ALICE experiment, where you see a picture of the quark gluon plasma that was observed at Cern. You can look in this beautiful event display of the tools that have gone into building this display, right? So people are needed who are working on the algorithms to prepare these displays, and they have to be ready based on the physics, based on the detectors that have been installed, and they should know every piece, every material, every geometry, and every feature on how this will work. Only then you will be able to create this beautiful display and also use it in some sense to reject or to keep data. So it's a very, let's say, structured work, and you can enter at any point. So it's not like, of course, you get a general idea and then you pick up what interests you. You can work on the hardware or you can work on the software, right? LHCb is the experiment that does B physics. Remember this imbalance for CP violation? And just, I think a couple of days ago, there was a press release about 59 new hadrons. Hadrons are just particles made out of quarks, and these new hadrons have been observed at the LHC. So it is indeed very, how can I say, humbling to be a very tiny part of this whole complex operations that are going on and somehow be related to whatever is happening at Cern. So yes, these are the 4 experiments, and for ALICE I mentioned to you already, for LHCb I mentioned also already to you. Now the other 2 are ATLAS and CMS. Those are the other 2 experiments. And lots and lots of work is going on. Let me just show you some pictures from the ALICE experiment. And here you can see Professor Anju Bhasin. She is Vice Chancellor and she is a physicist from Jammu Cluster University. And she's been working in this field for nearly 30 years as well. And I mean, you can again Google these people, they are doing amazing work. And on the bottom right, you see Professor Rashmi Raniwala. She is from the University of Rajasthan. And you can also see our Indian President's visit here, where Anju is explaining something about what's going on in ALICE. And on the top right, you see a picture which is looking forward to the upgrades that are happening in the ALICE experiment. So lots and lots of opportunities, as you can see. Now here you see another picture of a young lady from Punjab University who has been working on her thesis on nuclei and anti-nuclei production. And she also worked on hardware, where she made the detectors along with the team. Again, remember this, please, that we need to work together. We need to hold hands as well. This is very important. And only then can we move ahead and we learn from a person here and a person there. Every interaction is a learning opportunity. So whether you take it or not, it will be there, right? So again, so Natasha has been doing pioneering work in nuclear anti-nuclear production. So please again, Google her and you'll find her work. And I'm very proud to share this slide where PhD student Shaista Khan from AMU, she has been working on studying the net charge fluctuations in proton-proton and proton-lead and lead-lead and xenon-xenon collisions in data. So run 2, do not get confused. There has been run 1, run 2, and we are preparing for run 3 now. So loads of opportunities. She is at Aligarh in India, and they are working together with their colleagues, Bushra Ali and Dr. Hushnood. Again, there are many, many more young girls, professors and senior people, and I forget to mention also that's possible. I scrambled my head very quickly to find the names of all people that I would remember and I would include here. But it's also not a given that I know everybody. So please excuse me if I have forgotten to mention anybody. Again, we are back to our aerial view. So we have seen LHCb. No, not yet. We have seen only ALICE yet. So we go to LHCb. In LHCb, we have Dipanvita Datta. She is working on the radiative charm decay modes. for D to V gamma. She is working on many things, but importantly, she is also working on the state-of-the-art silicon detector at Cern, which is called the Velo, Vertex Locator. And she's been working there for quite some time now. I don't remember exactly how long, but she's postdoc, I think, in Manchester. Yes. Okay, so now let's move to the multipurpose experiments. Those are the Higgs hunters, so to speak, at LHC. So they are hunting for something, and you see the scales of these experiments. I already sort of hinted at that these are like many several storied buildings, and it's like a huge cylindrical onion, and if you cut this onion, each cell is different, so to speak, or let's say each layer can be similar, but then there are peculiarities in each of the cells, and they are looking for any signal that's coming out from the collision. And then when we put together all the information, we are able to recreate. Yes, it is an engineering challenge. How can a person, first of all, get the hang of the whole thing? It takes a while. There is so much jargon. You get so confused. But it's not that it's not doable. So you need just to focus on what you wish to do. Even driving equipment like this, standing on this lift that you see, it's called a lift, it's a scissor lift, and you can go up and down 20 meters and so on. So these are big challenges, and again, there are experts from everywhere that come together, and without this power of collaboration, we are not able to actually proceed. So here is another celebrated physicist from our country, Meenakshi Narayan. She is a professor at Brown University. I will not read out about her because she is very well known, and you are really encouraged to look at her career, and it has been a remarkable career, and she is on the top level committees everywhere at CERN and also in the United States. One aside is about communications, because that is extremely important. This is the reason why I am here today as well, because science communication is extremely important. We forget about it because we are so busy with our work, and there is also all the time this feeling of crisis management that we never finish, we need to do this and that. But a few minutes away from your normal work, it can make a difference to somebody else. And science communication itself is a career. And we have Paola Catapano from CERN, who is an amazing science communicator. Again, Google her up, and if you are interested in that career. And Paola Tropea, my friend, she is the CMS Deputy Technical Coordinator, and she is the Upgrade Technical Coordinator. Remember I mentioned things coming from Japan, from India, from United States, they have to all fit together, not only mechanically, thermally, in terms of, let's say that they are threads. So these threads should be in the same units. It's an unbelievably mind-boggling career, and it is possible. That's the main message. And we have our young girls who have taken up the challenge and who are actually working in similar fields. So Priyanka is a marketing fellow at CERN in the knowledge transfer department. Chetna is working in the communications. She was actually a student of engineering, I think, and she left engineering to follow science communication. And Richa is working in the administrative sector of the Science and Society Foundation. So you see, opportunities are there for everybody, and start where you are. You do not have to wait for anyone to tell you anything. Speaking about data challenges are incredible. I mentioned to you a bit about it, not too much, but you can only imagine that the amount of data, we are talking of petabytes here, that needs to be sifted to look for one signal out from the collisions. Out of all these million collisions that you have, then you have to pick out a single signal that is for discovery physics or the Higgs boson. So again, looking at careers, the software engineers among you, or people who like to work with machine learning and so on, you have a challenge right there. And data is also open, by the way. So CERN believes in open data, and the data has been published. So you can sit at home and start doing your analysis. Talking of triggering and talking of algorithms, we have our star Tulika Bose, who has been at the highest level in CMS as well, and she has been working on the commissioning of the CMS high-level trigger when we started taking the run one. So this again, when you look at it from objectively from outside, far away, you might imagine, what is this? But when you go inside it and you start studying it, bit by bit, piece by piece, it's actually possible. And she was also the physics coordinator of CMS, which is a very high level position as well. And she has been coordinating a record number of publications. In India, in Tata Institute, in the Saha Institute, we have celebrated scientists as well. Kajari Majumdar, she has been there from a very long time, I think, if I'm not mistaken, 25 years for sure, and she has been guiding umpteen number of PhD students, and she has done pioneering work. She was also the spokesperson of CMS India, and she has done amazing work. Please Google her. Naina Majumdar and Suchandra Datta at the Saha Institute also have been doing incredible work. So nobody's work is less, let me tell you. Everyone's work is out there, up there, and it is feasible when you start from the bottom, and you have to start from the bottom. We have Nishu, we have Monica, who are doing outstanding work, and they, at least Nishu, I know, she has gone to the other experiment, the Atlas experiment, and just to say that my experiment is the CMS experiment. And Monica has been doing incredible work as well. She's a postdoctoral researcher at the moment, and she was also awarded the prestigious CMS Achievement Award. So again, lots of physics work, lots of hardware work, and all is going on in tandem. We have Saptaparna and we have Shivali as well, who are working again at the forefront, but everybody of course starts small, and they have done very, very big contributions to CMS and to different kinds of, let's say, projects. Can't go into detail. Pallavi Das is also a postdoctoral researcher. She is working at Princeton, and she's working on the trigger operations, which is incredible, so to speak, because I always marvel at how people can do such complex algorithms and how we are actually making this data. You know, I'm a nuts and bolts physicist. I just know how to build the detector, and then after the detector, take the data and please give me the physics signal. What happens in between is quite a magic that happens, and I always marvel at people, and particularly women who are leading these kind of activities. Then you see Archana, she's Archie, we call her Archie, otherwise you might confuse her with me. So she's doing incredible work. She's a postdoctoral fellow at Aachen in Germany, and she works day and night at Point 5, which is our experiment, how it's called, and are again role models for young girls to imagine that yes, these careers are possible. There is Shilpi, there is Sudha, and all of them are doing a lot of work in both these experiments. Of course, they worked in CMS as well as Atlas because of the opportunities that they received. And I also wanted to highlight Prachi Atmasedha, who is working on the new small beads of muon system of Atlas, and she's been doing great work there as well. Oh, there is more. Sandhya and Deepthi and Swagata. So everyone is working in these experiments, and they have done loads and loads of physics analysis, and all the publications that you hear about, they all have a certain, let's say, input that is coming from our girls who have been working a lot in the software development, in the analysis, in the algorithms and searches and so on. Now, here is an engineer. Deepthi is an engineer, and she is working as a project engineer for the North area in the beams department. So this is something different. Although the picture shows CMS, but I didn't realize that she is actually in the beams department. So she should have gone in another section. Doesn't matter. We are always proud of our girls. Now here is a collision that was observed in CMS and in Atlas, and it's only one, but then in summer 2012, when the results were actually announced, we understood that this bump that you see over here was a bump demonstrating to us that it could possibly be a boson, and a boson that we knew called the Higgs boson. Different modes of decay are here. And we also have Seema from IISER Pune, who has been recently elected as a Fellow of Indian Academy of Sciences, who have and has done incredible work as a convener of SUSI in CMS, and she's really doing pioneering work. And any one of you who are close by in that region, you can always go and get in touch. So big day, July 4th, 2012, when there was this official announcement and an official seminar at Cern, which was followed live all over the world in Melbourne, where there was this conference going on, very big particle physics conference, where at Cern on the left you see Fabiola and Joe in Candela, who were the respective spokespersons of Atlas and CMS, where this was actually announced, the Higgs boson. And it also got the Nobel Prize in 2013. And you can see the number of people, and these are only the people who were present at CERN. And think of the people behind back home who were also part of this journey and were really, let's say, contributors to this Nobel Prize when this was awarded to Francois Englert and to Peter Higgs, of course, Professor Peter Higgs, right? And this is our team in India, the CMS experiment, and you see many, many women right in front. There's Professor Manjeet here also, Suman Beri as well. I cannot go through all the names as you can imagine, but this is fantastic to know that big science really wins a lot of Nobel Prizes, right? And being together is very important, and being, let's say, CERN model of working is what we need to take. You know, not everybody can be at CERN, but we can all together. And this has another role model here that I highlight, who is Charlotte Varakaule. She is the first director for international relations at CERN. And this is extremely important, as you can imagine, because coming from different countries, we need to support fundamental science in every country, keeping it at the highest priority. That is very important. And there she excels, and she's really particularly been, let's say, conscious of the fact South Asia represents a very big potential, and we have had several events at CERN, outside CERN, where she has been a key player in facilitating those events. Now there are new projects at CERN on the horizon. LHC, you heard, high luminosity LHC is the upgrade, where there is of course a lot of room to engage. Lots of data already exists. The future is coming. So girls, it's really time to engage and to look at what's happening, what's coming up. What is this new project called the Future Circular Collider with 100 kilometers circumference around Geneva? It will dwarf the Large Hadron Collider. So it is time to engage. And how, excuse me, and how do you think that we are going to engage? We should engage, or we should try to engage in what interests us. So we need to look at what's going on. Am I really interested in doing physics? Or am I interested in doing the engineering? Or am I interested in becoming an entrepreneur? So please look around and see what are the highly demanded industrial sectors in India. And you might want to just hook your interest on that side. There are many, many opportunities there. And as you see on the bottom left, you see there's a school in Mumbai called Podar School, which had the winners of the Beamline School competition from CERN in 2018 came from Podar School. Dipandita here, she's a beam physicist. It's incredible. She is running the beams. She is overseeing what's happening in these large halls, and she is chair of a working group which is coordinating all the activities in the different projects. So this is incredible, and I'm very proud of her as well. And then we have Hiral as well, who's a BTech in mechanical engineering, and she is also working as a technical student at CERN in the beams department. So loads and loads of opportunities and loads of, let's say, learning, upskilling, and so on. So if you are a particle physicist, you know, like me, I'm a nuts and bolt physicist. You can be any of these careers that you see right in front, because particle physicists create a new value. And the growth is multidimensional, and it is very multidisciplinary. And you can engage in any of these any of these phases of a project, because there is a creative period when you just think about a project, then you develop prototypes, you study, you do some R&D on it, then you execute the project. Sometimes it takes 10 years to do that. Then you monitor the data that's coming out. Sometimes you get a physics discovery, and so on. So I think I don't need to go through the whole circle to tell you that how far reaching particle physics is, and you will find an intersect which interests you. Now let's see, on the bottom left you are looking at a picture, and this is the imaging picture done by a sensor that was developed for physics, for particle physics at Cern, in collaboration, of course, again with many large number of institutions. So yes, I hope that I managed to confuse you a lot. Just like my son, I was also very, very confused when I started my career. I was very unclear. People used to joke, you are studying nuclear physics? It is totally unclear. It's okay. उसके ऊपर से, as a girl, when I decided to study nuclear physics, when everyone was doing electronics or software, I was again ridiculed, so to speak, because in my days, in the 80s, nuclear physics was supposed to be only for the boys. It's a very difficult subject. तुम क्या करोगी पढ़ के? तुम physics पढ़ोगी? तुम झोला लटका के जाओगी? All sorts of things you will get to hear in those days. But you all are lucky. You are in a time when it is recognized that any career can be taken up by a woman as well. So yes, this is an impossible dream, but I want to share with you, because in 2009, in the holidays in December, I dreamt of a project. Okay, I kept at it, I worked on it, and in 2012, finally, I was allowed to write it down and submit it as a project to the management. This photo is coming from 2019, or was it? Yes, 2019, when we are installing one of those detectors that I have proposed in 2012 into CMS. And again, it is not me, it is the whole team that has come together. And you can see here that this is really part of the team because of the COVID. But we are more than 16 countries, 300 collaborators, and lots of young people around. And as you see, many girls here as well. So you saw how nicely it was installed, and in the end, it was really like a big achievement for our collaboration, that despite the pandemic, able to install this detector. And last year, we also won a small prize, not big, for this particular feat. And there's lots to do, of course. So I hope I've convinced you that the curiosity about universe is really impacting millions and billions of lives. We have many projects coming up. There are lots of opportunities, but what you really need to do is to upskill. Upskill in line with national priorities. And how can you upskill? In India, there are loads of opportunities, many big laboratories, institutions. We have had incredible scientists in our country. So you just have to follow the footsteps. Look at the Sustainable Development Goals of the United Nations. Align yourself into what you believe in. If you believe in helping other women, help them. You are working on the gender equality Sustainable Development Goal. Good health, techniques, sensors from particle physics are going into the Sustainable Development Goals as well, and so on. So there's no dearth of what one can do, and you just have to engage. That's important. Okay, so I think I've come to the end of my talk, and I'm very happy to be here with you today. And seriously, there are lots of opportunities, and the best is around the corner. We have just started the journey, and I'm really very, very happy to answer questions now, or if you have any remarks, I'm happy to take them on board. Thank you very much.
Thank you very much, ma'am, for this wonderful lecture and wide discussion. I think you have covered most of the topics, and that's why audience don't have much questions. But still, if the audience have any questions or comments, they can put it in the Zoom chat. For the participants who are attending it through Zoom, I will invite questions from them, as well as the audience who are participating through Facebook Live. They can post their comment or any questions in the comment section. I will take either of them, but as there is no more question, at least up to now, I think it will be worth to discuss maybe different kind of outreach activities by Cern, like their summer programs and their programs and openings for the undergrad students. Maybe you can speak some lines about that.
Definitely, Uma. Thank you for the question. Indeed, all young students who would like to engage may want to look at the website called careers.cern. And there you will be able to see the number of opportunities for students. And these opportunities are starting from being an intern to being a summer student, which is about 14 weeks, if I remember well. There is technical students program, there is doctoral students program, and and of course there are many lectures that are constantly happening at CERN, even technical lectures that are completely free. So you are all requested to please go to careers.cern, and you will be able to just navigate and look at the opportunities.
Okay, there is one question. Is there any scope for the students from the chemistry background?
So there is a lot of work going on, for example, on detector, and these detectors have a lot of materials, and these materials sometimes need a lot of how can I say analysis. And for these analysis, there we have a chemistry lab, and in this chemistry lab, there are many spectroscopy instruments, and certainly there are. I did have a couple of students from India, from chemistry background, who have done their internship at CERN.
Thank you, ma'am. Okay, I don't see any more question. Anyone from Zoom? Okay, there is one question in Zoom. Okay, as a VLSI master student, how can I pave my path towards Sun?
So there is lots going on in India. First of all, let me tell you that the detectors I mentioned, I didn't go into detail, but there are lots of silicon based detectors into in CMS, in LHCb, in Atlas, everywhere. I mean, silicon is used everywhere. So as a VLSI graduating person, I think you really need to hook on to what's going on in India first, what's happening in the foundries in India. You look at the work done in the collaboration, in the context of a collaboration between India and CERN, and that there is your hook to go and start learning and then contributing, participating, and becoming part of the collaborations that exist at CERN.
Okay, we have one more question. What are the possible application in the field of space science?
Absolutely. I mean, I didn't have time, but I could show you some pictures where detectors that have been invented at CERN, they are being used in space. So you know that when, even in the ISS, by the way, I do have a wonderful picture. I didn't have time to put it together, but the pilot wears a detector which will measure the dose that he gets when he is orbiting. Okay, and the dose can be measured using a silicon detector that's called Medipix. Take a look at Medipix, Google for it, and you will find that's one application. Apart from that, there are many sensor applications for our detectors, and they are used in space experiments. You may know the experiment called AMS, Alpha Magnetic Spectrometer, that is on the ISS as well. And just take a look, lots of applications in space. And also material sensors. I mean, kt.cern is another, what shall I say, place where you can go to look for information. And there is something called space applications. kt.cern is knowledge transfer, and there's a lot of space application area inside kt.cern. Oh, please, I made a mistake again. kt.cern, not ch. I'm too fast sometimes. Sorry. It's kt.cern.
There is another question. She's asking about the career opportunities for a material science student at CERN.
So again, I mean, detector development is very broad. First of all, you need to find materials that are actually workable for the work that we do. And it's not only in the sensors, but they are also, let me give you an example of aluminum nitride that is being used. There is also another example of carbon fiber. Carbon fiber is now widely used as a support material, very strong support material for our detectors. So the tracker itself, I don't know how many tons it is, but the support is a carbon fiber composite. So indeed, I think in India there are people working on this, and you should just Google a bit and find them. Okay.
Okay, I see more questions. What new dimensions will be opened for the physicists during the third LHC run as well as for the FCC?
I'm sorry, I missed the first part of the question, Juma. Sorry.
She is asking about the new dimension that can be opened for the physicists during the third LHC run and as well as for the FCC.
Certainly. I mean, the open questions are still there. We are looking for dark matter candidates. So, Susie would be great if we can find some candidate particles. And in general, I mean, there could be surprises, or we could just be fine tuning and measuring very carefully studying the Higgs. I mean, it's a new particle, let's say, we have not studied it to great detail yet. The production rates will increase, so it will give us opportunities to look at new decay modes. One of them has just been published, I think. This was with four leptons. It was very recently, four leptons and a photon. That mode has never been seen before, and that was very recently. I think it's not even a week old news that this has been observed. So run 3 is coming, yes, but run 2 data is sitting there. You please hook yourself there and get started. You might find something new there, and have a press release on that.
Okay, this is a different kind of question. She is asking that most of the students have no experimental experience in particle physics but want to pursue physics and are not being selected. How one could proceed with this?
Absolutely correct. I mean, I fully agree with this frustration, so to speak. It's a disappointment when you apply and then you are not selected, and believe me that I was rejected at least from 100 places. Okay, so it's do not be disheartened. First of all, that is my first message. Second message is, in our country there are so many things happening in mega sciences, and there are a lot of experts in our country. So you need to figure out in the field that you want to work in, where are the experts, and just try to go and spend few months there, even if it is for free. Don't think about think about making a career, not about just getting a job at this moment if you are a young student. So the moment you will be there for, let's say, 2, 3 months, first of all, you will be reinforced whether you really want to go for research or not. Because it is a tough career. And you need to be convinced that you absolutely want to go for it. That's the first thing you will get. Second thing that you will come to know immediately just by the fact of being in a larger group, you will know who's doing what kind of activities are going on, silicon, software, hardware development, materials, all these kind of things you will get to know in your exposure of 3 months. You just need to find a good mentor in the country. The moment you are engaged and you realize what's going on, and if you want to be part of that group, that is the way to go. The moment today the world has shrunk, you can see the pandemic has given access to everybody. It has completely democratized knowledge. Nobody is left out. Everyone can connect to anybody. So this is the big thing that we have today. The moment you are convinced that you want to work on a certain subject, please do not hesitate to contact people. Don't be shy. Even to ask questions, don't be shy. ये time लगता है इसमें थोड़ा, I fully realize, because I also went through the same cycle, but at least you can be in an accelerated mode and no need to wait 10 years to become fearless to ask questions at least.
Okay, one of our audiences have question. She works with combining spectroscopy data and then applying it to the machine learning. Is Cern providing any opportunity on it? This is our question.
It's for learning. Is that correct? The question is on learning.
Yeah, machine learning. She is working on the spectroscopy data and its application to machine learning.
Machine learning, acha, I see. Definitely, there are so many resources. The problem with the web is that you have so much of information that you are unable to navigate to the right part. So there is a communications and education department of Cern. Please go there, and I think it's called education, communication, and outreach. Yeah, outreach. That's how it's called. Just Google there and you will find so many resources, and you will even find people who will be able to answer your questions in a better way than I can do, because I'm giving you just let's say, a generic information. But you need to catch people and you need to get all these resources, and they are freely available also, right?
Someone else has a similar question. She's working as a full-time professional, working in the data science and machine learning. So she was also inquiring about different opportunities that are available in that area. So I think you can also refer to that site, her. Okay.
Yes. And I have given you the names of so many women as well. So I think please do feel free to contact them. They are all very nice people. And the one big thing is that we have to hold each other's hands to move ahead. We are less than 15% when we look at the global picture. But in the younger stages, they are like 50%. So we need to enable everyone to move ahead. So I'm very happy to say that at least in these mega science projects, we really hold hands and we really move ahead together. So please take advantage of this and get in touch with all the women I've mentioned, and some of them I hope will answer, and you will get what you as you're up.
Okay, I don't see any more questions. I think I have taken all the questions from the Zoom. Yeah, I'll just check once that I'm not missing any. Yeah, okay, I think I have covered all the questions. Okay, Facebook, there are no more questions. I'm very happy that many people have asked questions in Zoom as well. They have interacted quite well, and also I know that many people are probably shy and they don't want to ask directly. Okay, but I'm happy that we have interacted with some persons, and if this lecture and the other lectures of this series have helped them to explore those careers opportunities. If they have helped them to find out some way in the career, because it's quite confusing. So that was our aim of this online lecture series. I want to thank Dr. Archana Sharma, the last speaker of our online lecture series on this special day, this 8th March. And as we will end this online lecture series, I want to thank all the audiences for showing their curiosity, who have joined, interacted, and listened to our lectures. I hope they will also be with us in future for all the other programs. And I'd like to thank everyone once again. And if you have missed any other lectures or you want to attend the other ones, you will find all of them on our Facebook page, Nehru Science Centre Mumbai. If you go to the tab live, you will find all the 7 lectures in different 7 meta science projects on the similar topic. Um, do we have any questions? Okay, I see a few more questions. Okay, I'll take one last question. Can the silicon detector technology be extended to using fibers, which are relatively cheap?
Do it.
Yeah. Okay. Now I want to end this here. Thank you very much.
Thank you, Juma, and thank you everyone for attending the lecture as well. Okay, thank you. All the best. Bye bye.